Hola, chaps. Let's learn. Hola, chaps. Mr. Turk here. This is primarily for CP Physics on study of static electricity, but the rest of you can enjoy this as well. There's a handout called Charging Objects, and it's got a series of experiments for you to carry out. I'm going to try to do them myself. It says, blow up a balloon, tie it off, and rub it on your head. Actually, that's a serious statement. So here's the balloon. And rubbing it on the head, of course, is rubbing it where there's lots of hair. So this is going to be a little bit of a challenge to make it successful. Maybe I should go use my wife for this part. But let's see, after what, 2 months of lockdown, rubbing it on your hair should be pretty easy. And maybe you can even see that on this video, if I get my hair just right, you can see that it's responding to the balloon, right? So when I bring the balloon near my hair, you can see that my hair is standing up as the balloon comes near it. So that's the purpose of doing this. The rubber balloon is an insulating object. And America's first scientists figured out that when you rub one object against another, electrons are actually scraped off one object and onto the other. So there's the first step. And here's the part of the balloon where I have scraped electrons off of one and onto the other. So the next step, unfortunately, I didn't mark that spot. So if I drop this balloon, it's kind of like, what's going on? So next up is to take a piece of reference tape and see how it reacts when you bring it near the balloon. I remind you that the reference tape, by definition, is negative on its sticky side. And as I bring it near the balloon, you can't really see what's going on very well. And I feel like the reference tape is not doing its job so well. So yeah, it's a good thing I have lots of hair on my head. Remember, I'll fail you if you. Anyways, so looks like I'm at the end of the roll of tape. I'm going to try this one more time. So here's my reference strip. Here's my rubbed balloon. And when I bring them near to each other, I think you can see that. The tape is definitely attracting to the balloon. Okay? The tape is definitely attracting to the balloon. So there's our reference. The negative side of the tape the sticky side of the tape is negatively charged, and it attracts to the balloon. So you should be able to figure out, therefore, the balloon is positively charged. We're going to go forward with that. So on this handout, it begins with the first question for you to fill in. What is the charge on the tape? Well, of course, let's see if you could see the question a little bit better. It's negative. What happens to the balloon and the tape? They attract. So what's the charge on the balloon? Opposites attract. So eventually you're going to write out the word positive. And here we draw the charges on each object. This represents the reference strip, the tape. So it should have some negative charges on it. And then for the balloon, overall, it was originally neutral, but as I rubbed it on my plentiful hair, it scraped electrons off the balloon, particularly on that one region of the balloon. So here's an area where electrons have been removed, and therefore what's left behind are the positive charges that are stuck and can't go anywhere. And then far away on the balloon, there's still electrons and protons are everywhere. So maybe back here, I could show that it's polarized, but neutral-ish in this region, electrons being repelled from electrons. Here, electrons have left the entire area, and it's a positively charged balloon. So yeah, this is a great way of combing my hair. Oops, whoa, I should edit that one out, right? So I'm going to do this again because I forgot which part of the balloon is positively charged, and I'm trying to hold one region of it. So that area is positively charged. All right, number two, next thing. It says, look at the confetti on the table. Well, so it's time for some confetti. You can create confetti yourself by finding a hole punch and then punching a bunch of holes and then opening up the base of it. Opening up the base of it, which will spill out a bunch of little confetti pieces for you. There. So I got a bunch of confetti, and you should be able to see them on the piece of paper. Look, different colored items. And what I'm going to do is move the camera down into the field of view at an angle, and then shift this up here like this, tilt this a little bit more so you can see it directly. So I'm going to remind you, you've got two viewpoints going on here. You've got the camera coming from this point of view and being projected on the screen, and you've got your webcam coming from this point of view, seen from the side. And so I bring, well, actually, it says, look at the confetti on the table. Notice the interaction between the pieces. What do you observe these pieces of confetti doing? Yeah, that was a pause for you to actually write it down yourself. And the answer is nothing, nada, zilch. Nothing is happening. So what is the charge on the pieces? These pieces of paper that are just chopped up and sitting there, neutral. So what should I draw for each little circle here that represents a piece of confetti? And you should say, well, I should draw it neutral. But if I put a plus on one and a minus on the other, that's not neutral. And if I put pluses, one plus and one minus on each one, that's neutral but polarized. So you need a miniature checkerboard pattern: plus, minus, minus, plus, plus, minus, minus, plus, minus, plus, I don't know, plus, minus, minus, plus, plus, minus. So there, a checkerboard pattern for each of the little pieces of confetti paper. And now it says, when you hold the balloon over the pieces of paper, what does the paper do? So here we go in the name of science. I believe you can see that on the side camera a little bit better. And you can see, some of the confetti is sticking to the balloon, actually. Okay, so that's very important. A lot of the confetti sticks to the balloon. Okay, so that's what you should write down. When you hold the balloon over the pieces of paper, what does the paper do? Jump onto balloon. Great. What type of charge would you assume the confetti to have? You're going to give a wrong answer, aren't you? I know it because, I've been teaching this for many years, longer than you've been alive. But okay, so the point is, you're going to say you assume it has an opposite charge because opposites attract. But think about what you allegedly drew, or what I drew for you. We drew that the paper is neutral. It was not charged. It wasn't interacting with each other. It's neutral paper. And when I bring the balloon near it, guess I need to recharge it. So if I rub this on my hair, then I'm going to end up with confetti in my hair, right? Yeah, okay. So, yeah, I'll just keep doing this because it's, restful and relaxing to demonstrate science processes that work for you. Good thing I have hair to do this with. Yeah, lots of it. That's why I do volumizing shampoo all the time. All right, so what does the paper do? What type of charge would you assume the confetti to have? You foolishly would assume that it has, I suppose you would answer that it's opposite of the positive charge. But if you want to put out a correct answer, the correct answer is neutral, but polarized. Okay, on your own, you would probably put down negatively charged. But let's see what the sentence says for this little interaction. It says, when the positively charged balloon, well, duh, see, I'm following the expectations here, is held close to the neutral confetti, the negative charges in the confetti are attracted to the side of the pieces nearest the balloon. This is called induction. Okay, so what is induction? Separation of charge without touching. Okay, so let me go over that again. The confetti is neutral. The balloon is positively charged. When I bring a positively charged object near a neutral object, the charges that are like repel and move farther away. The charges that are opposite are attracted to each other. Now, the positive charges can't move, so I shouldn't say, the positive charges move closer. It's only the electrons that are moving. Either they move away because there are other electrons, or they move towards because there are fewer electrons. And where there's fewer electrons, there's more protons and therefore opposite charge. So what's going on here, induction is a situation where I have a charged object. And by the way, it's not going to matter whether the charged object is positively charged or negatively charged. The effect is still going to be the same. When I bring the charged object near a neutral object, the effect is like charges move farther away, opposite charges are closer. And in the tug of war, based on Coulomb's law, the strength of the charge falls off as the distance increases. So the farther the separation, the weaker the force. So here we have a tug of war going on where the closer charge is always the pulling together force, which is smaller r. The repelling force is a larger distance, and therefore the weaker force. So of this tug of war between attraction and repulsion on a neutral object near a charged object, attraction will always win. Again, it doesn't matter if it's positively charged or negatively charged, it's going to be the near charge is the attractive charge, and that will be the stronger charge because the distance is shorter. And therefore, a neutral object will always attract to a charged object. And that's what's going on when I charge up this balloon. So it's got positively charged. I bring it near the confetti, and you can see the confetti just loves to jump onto the balloon. It's aiming for those areas where electrons were left on my hair, right? Because the balloon is positively charged, so I have extra electricity on my head right now. Woo-hoo! Okay, that and coffee will have the same effect. So the neutral confetti is an insulator, the rubber balloon is an insulator, and the paper confetti jumps onto the balloon, hoping to land at a spot where electrons from the neutral confetti can at last hook up with the opposite charge that they're attracted to. And maybe in some cases they happen to hit just right and get electrons to leave the confetti paper and go onto the balloon. Now, that leads to an interesting, outcome. So what happens when a neutral object loses electrons? Yes, you should be saying a neutral object that loses electrons becomes positively charged, and the balloon is positively charged. So maybe, that would account for what you see going on here, where they don't all just stick and stay, right? They all jump up. Well, many of them jump up, but notice that they don't all stick, right? So here we go one more time because it's fun to watch. And maybe I'm losing my hair. Nah, okay. So next, try the same thing with pieces of foil. So I'm going to lose my place with this balloon, but excuse my reach. I went to the kitchen and got a piece of aluminum foil, and I took some scissors, as I enjoy mispronouncing it, some scissors, and I chopped them up into little tiny pieces, lots of them, right? 4, in fact. And these are not actually tiny pieces. So you can see here on the main camera that that's where they are, and I'd have to move this camera this way, and you can see them there. So they're really not tiny pieces at all, as you can see using my finger for scale. But, so what's it saying in directions? It says, now try the same thing with pieces of foil. When you roll the foil up into little balls and hold the balloon over, what happens at first? Okay, I want to override the instructions and say don't roll it up into a little ball. Leave them as little flat pieces. And here, let's recharge the balloon with my voluminous hair. And foil, in case you're not too familiar with it, is a metal conductor. So will something happen that's the same or different this time? Here we go. Observe in the name of science. I think you can see on the main camera what's happening, and this is not the expected outcome, by the way. So I'm going to try to have these things get off. I can tell you what's supposed to happen, which is, pretty important. And of course, if I were to test you on this, assess you, so what actually happens, don't tell me what actually happens. Tell me what is supposed to happen according to all the principles of physics that we try to teach you. So here I have a positively charged region on the balloon. I bring it near the allegedly neutral pieces of aluminum foil, and the foil, there's a good example, jumps up, jumps down, jumps up, jumps down. Better than the paper does. Ooh, there's one that stood up for a bit. Okay, so sorry I can't zoom in a way that lets you see it. Either this angle is blocked by the camera, or I mean by the balloon, or you just have this distant view from there. So work with the distant view. I don't think I can bring it that much closer to your camera and have you see what's going on. I guess I would just say you can probably see that okay. So once again, charging up the balloon with my voluminous hair, I bring it near the aluminum foil and try to observe. I got one to stand up. It jumps up, hits the thing, and jumps off. Jumps up. This one's stuck, right? Jumps up, generally jumps off. So what happens if I have both foil and confetti all mixed together? This is something that we've never done before in my 27 years of teaching physics. First time ever science experiment, right? So I'm going to go ahead and recharge the balloon and bring it near, and let's see what happens. A little hard to tell. Ha! Look, only, I guess, I'm trying to zoom in. Look, the circles are the confetti. Only the paper confetti stuck to the balloon. The foil jumped onto the balloon and generally jumped off. So we've got one, what do you call it? Trader here who's joining the other tribe. So I have one piece of foil and lots of pieces of paper stuck to the balloon. And let's finish off the sheet and then pause for a moment. So setting the balloon aside, setting my confetti aside, putting the sheet where you can actually see what's being displayed. For educational purposes, let me try to explain to you what you just observed. Get the camera out of the way, scroll down. Here's the expected answers. I'm giving you the answer key. This is like a free education, right? Just bring your own container. All right, so tried the same thing with the pieces of foil. It said, don't roll up the foil. And I could zoom in just a little bit more. You can still almost read the entire sentence, just barely. All right, so what happens at first? At first, okay, so this represents the balloon. This represents pieces of foil. Now, the foil, I remind you, is allegedly neutral at first. So I draw the region of the balloon as being positively charged, particularly in that area. Now, the rest of the balloon, you could draw it as being polarized, but neutral, something like that. Okay, fine. Really, it's this part of the balloon that we care about, the part where I scraped electrons off of it. That part is positively charged. What is the charge on the foil? So what you should realize is that it's neutral, just like the paper confetti. If it weren't, then when I have a pile of debris here, where can I move it that you can actually see it? There, found it. So if these things had electric charge, they would be interacting with each other like crazy and either attracting or repelling. But all you see here is a pile of round pieces of paper and rectangular pieces of metal, aluminum foil. So they're neutral. Yet when I bring it near the balloon, stuff happens. So what I should really be drawing here in this first part is that it is a neutral but polarized object. And that means the electrons move towards the balloon. So the side of the foil that is closest to the balloon is negatively charged. The side of the foil that is farthest away from the balloon is where electrons have left that region, leaving protons behind that have no balancing negative charge. So overall, the positive charge is left behind. Same thing with this piece of foil. So here's two different pieces of foil, and they are both being attracted to the balloon because neutral objects are attracted to charged objects. So what do the charges do in the foil balls? You could say they polarize. Now, polarize is a word we used in our study of waves, and it meant that I have an electromagnetic wave with two different orthogonal components to it, and I can filter out one of those by passing it through a polarizer. In static electricity, polarized refers to a neutral object where instead of the charges being evenly distributed everywhere, they are separated out by induction, by the way, so that one side of it is one charge and the other side of it is the opposite charge. Okay, so that's polarized. I've drawn the charges in the foil already. Let's move on. What happens after the foil makes contact with the balloon? Okay, short-term memory quiz. What just happened about 3 minutes ago in the video? Of course, you remember. Once the foil touched the balloon, it jumped off of it. Okay, so uh, foil jumps off balloon. Ta-da! Okay, education. What type of charge would you assume the foil to have? What's the one condition that would make objects repel from each other? Knowing that one of them is positively charged. Knowing that the balloon is positively charged. What would you assume would be the charge on the foil, which is repelling the balloon? Of course, it's positively charged. Great. So when the foil makes, and here's the explanation, when the foil makes contact with the balloon, charges spread out between the objects in contact. This is called conduction. Conduction occurs in metals. Conduction, charges transfer by touching. Okay, there it is in my own words. You were supposed to do this in your own words. And now look at this drawing. So here's a misconception you students tend to have every school year that I teach this stuff. It goes, oh, well, if I have a charge and let's say I have a negatively charged object and it gives away some electrons, then afterwards it must be positively charged or it must be neutral. Both of those are wrong assumptions. So let me explain. Here's the balloon. It's positively charged, and I only drew 3 charges on it to represent that. In fact, I totally forgot this part. You should be doing this one, right? So this was a positively charged balloon back here. I forgot to fill this in. These things here are neutral. But polarized. So negative closest to the balloon, equal amounts of positive charge, farthest away from the balloon. Okay, so neutral but polarized. And what I should show here is there's actually a little interaction that takes place here. You know those electrons I told you about? They can move in a metal conductor. In fact, that's a definition of what a metal is. Definition of a metal is an object that allows electrons to flow freely through it. An insulator is a substance that doesn't allow electrons to flow freely. So what I could add to as an enhancement to this drawing is a little arrow showing electrons going from the pieces of foil onto the balloon. So I'm trying to show somehow that electrons are jumping from the foil to the balloon. They can do that because the foil is a conductor. Unlike the paper, where an electron can't move very well, on the foil, the electrons can move more easily. And in this case, they're trying to fly towards a region on the balloon that has positive charge. And when they get there, if their targeting is good, then the electrons can actually leave the foil and go onto the balloon. So here's the misconception students have. It says, oh, I have this positively charged object and I add electrons to it. What is the charge on this object afterwards? And usually the answer is, oh, it's neutral. Or another wrong answer, oh, it's negatively charged. So let me explain now. Put some numbers to this. Let's say that when I scrape that balloon against my hair, I scraped off 100 electrons. Okay? So that's how much positive charge was on the balloon. And now, when these pieces of foil arrive, let's say collectively, they transfer over 10 electrons. Okay? So I had taken 100 electrons off, and the foil puts 10 electrons on. So a neutral object has neither positive or negative charge, equal amounts of positive and negative charge. When I scraped the balloon on my voluminous hair, I removed 100 electrons. When the foil lands on the balloon, it gives it 10 electrons. But how many does it have now? Well, it had negative 100. It was down. That's what attracted the electrons to it. So, whoa, they need electrons. Let's go to the rescue. And when they get there, they deliver all that they feel like doing or are capable of doing. They give them 10. So the balloon is still positively charged. It's just less positively charged. Instead of positive 100 charge units, now it's down to positive 90 charge units. And meanwhile, what is the charge on the foil? It was neutral before it got to the balloon, but now that it gave away 10 electrons, it is now positively charged by 10 charge units. What do like charges do, pray tell? I have a positively charged balloon, and now that the foil has given away electrons, I have a positively charged foil. Like charges repel. Ta-da! This is what you allegedly observed, that the foil, when it gets to the balloon, transfers charge, and now like charges repel, and off it goes. Now, when it hit the tabletop, it might well have become neutralized again, letting it do multiple jumps. I'm neutral, oh, I'm attracted, oh, I give away my electrons, it's still positively charged, like charges repel, go away. Oh, I touch the table, I'm neutral again, and the cycle repeats. Ta-da! All right, this seems like a good stopping point. I've made it halfway through this handout. So I've done the entire front side of the handout. I'm not sure if I should continue this one. Let's make this maybe as far as I go with this particular video. And then you guys try to anticipate the backside of the handout. I'll give you a preview. It says, oh, take some PVC pipe if you can find an irrigation line in your yard, dig it up and use it. That's a joke. You might find some scrap PVC and wool and use that together. And for a pith ball, you don't even know what a pith ball is. It's cork. You could go down to Newport Beach, where they have cork trees and try to extract some of the bark from the trees. Or, much simpler, if you happen to have a box of Cheerios or a very close equivalent, they work as well. So a pith ball, you can substitute a Cheerio hanging on a thread. So that will be the backside of this handout, and now appears to be an excellent opportunity to shut off this video for now and have you contemplate the next episode. Ciao.